Hi, everybody. So I'm the ghost of Alistair Sinclair. I've come down from heaven to tell you about the Simons Institute. So if you don't, Alistair Sinclair is alive, but I'm still his ghost. There's two of them. So I'm the ghost of Alistair Sinclair. It is my job to tell you that the Simons Institute was founded in 2012. Hundreds of millions of dollars were involved. And as part of that, I asked you to protect the place. So if you are eating in here, that's bad. If you have coffee in here, that's bad. I've been told you're allowed to have water. And this semester, so Bing Bin is extremely politely standing on the threshold. Like if you move your hand in, that's bad, but if that's very good. And by the way, for those of you that weren't here when Alistair was here, like he did a lot to sort of protect the place and make sure the clocks were on time. So it's very important. Also say that, so for those that are just visiting for the week, we have 2 ML programs for the semester. And so you're willing to come, you're very welcome to come upstairs and hang out with us. We have a lot of people doing a lot of cool stuff, not just Ankur Moitra, but of course, we're very happy to have you start the workshop. So the other thing I'll say, logistical, so in addition to the food and the drink, is that there are lockers just outside on this floor if you want to keep your stuff here. So I'll hand it off to Adam, who organized the workshop this week.
Thanks, Matus. And thanks, Matus, for helping me organize the workshop. Matus is awesome. I wanted to thank him. Real briefly, for those who don't know me, I'm Adam Clivens. I'm the director of IFML, and you can go to ifml.institute to see all the cool things that we're doing at IFML. This is the 3rd joint IFML Simons Symposium that we've had. And I think it's, I was thinking back when I was a graduate student, way before you, in 1998, like there was no Simons Institute. And so, you know, if you wanted to network or, you know, catch Avi Vigderson and ask him a question, you had to go to Stalker Fox and try and corner him somewhere. So I think, you know, Ankur asked me, like, what's the theme of this workshop? And the theme for me, whenever we hold these, is just giving students like you guys an opportunity to talk to, you know, people like Ankur, Poling, you know, in the back there, you know, more established people in the field, get to network, ask them questions. So it's a great opportunity. I am happy to introduce Ankur to give the first talk. Ankur, when I asked, you know, people at breakfast today, like, what are you most looking forward to at the program? Everyone said Ankur Moitra's talk. So, you know, don't want to set the expectations too high, but Ankur always gives great talks. So, you know, it'll be easy for him. I do want to say, again, thanks to Matus, thanks to Shafi and Sampath, thanks to the Simons event staff. They always do a great job for hosting us. So let me turn it over to Ankur.
All right, everyone. So thanks for coming in the morning. So I'm going to be talking about learning from dynamics. This talk is really about a very basic problem in control theory that's been open for a long time. I'm going to give you new algorithms for this very basic problem. And I should tell you that this is based on joint work with some awesome collaborators. So Ainesh Bakshi, Alan Liu, and Morris Yao. So because we're certainly not all control theorists, I want to start off by explaining what a linear dynamical system is. It's really just an abstraction that's captured by these 2 simple equations. So let's go through it slowly. So the idea of a linear dynamical system is that you have a hidden state, xt, that's evolving over time. Now, also your linear dynamical system is subject to some kind of control that changes its underlying hidden state. That's a vector ut that you might see. That's the input to the linear dynamical system. And the catch is that you don't actually directly see the hidden state. Instead, what you get is some sort of indirect linear measurements of the hidden state. These are my observations, y2. So now in these 2 defining equations, each of the matrices that show up are very important. They play a very special role. In fact, they have particular names. So the most important of these matrices is A, which is the transition matrix. This describes how the system would evolve on its own in the absence of control. But we also have things like the control matrix B that describes the relationships between how inputs to the system change the underlying hidden state. And finally, we have these sensing and feed-through matrices that just described the linear relationship between my observations and the hidden state and the control. Actually, to keep things simple in this talk, you can ignore D if you want and just pretend it's 0. Now, the last piece of this equation is that the entire process is not deterministic, it's stochastic. So in fact, I have two noise terms, one of which is called process noise that affects the trajectory of the hidden state. And then I have observation noise because my observations aren't perfect linear measurements, but maybe they're approximate linear measurements. So these are the two equations that I'll be interested in for the entirety of this talk. But what I want to do first is I want to try and explain, why this is such a powerful abstraction. So there are really lots of places where these models show up, maybe the most famous of which is in areas like navigation and also in robotics and tracking. So here, it turns out that linear dynamical systems are actually instrumental in the literal moon landing. So the algorithms that are used for performing inferences with linear dynamical systems were actually built into the spacecraft. And here the idea is that I've got the spacecraft traveling from the Earth to Moon. And at each time step, I get some very noisy estimates of where it is, which is the thing I want to know. And now I can do all kinds of things like ask whether there's a way to take these very noisy measurements and use my knowledge of physics to try and denoise them to get smoother estimates of my underlying trajectory. But at the end of the day, what's going on is that you have a linear dynamical system. So in the abstraction I gave you on the previous slide, what's going on? How does it fit in? I have this hidden state xt that describes all the things I want to know about my spacecraft. It describes the position, velocity, and acceleration. And now my transition matrix is really just comes from the laws of motion because it describes the way in which the velocity changes the underlying position and the way that the acceleration changes the underlying velocity. So when you think about discretizing the laws of motion and getting this transition matrix, what you would end up getting is actually something that's upper triangular with ones along the diagonal. And that'll be an important example. So just keep that in mind for the things that we talk about, later on. So this is one famous example. So not only was, the Kalman filter, which is really revolves around linear dynamical systems used in the moon landing, it was awarded the National Medal in 2009. So very, very impactful thing. Now, there are other cases where linear dynamical systems arise, maybe where we don't have such a first principles way to think about, what are the parameters of my underlying system. There are also ways that, show up in natural processes like biology and epidemiology. So in fact, there's one particular application that unfortunately we've all become way too familiar with over the last few years, which has to do with the spread of viruses. So what you can do is you can think about your underlying hidden state, xt, as describing among your population, how many people are in each different category. Are they susceptible? Have they been exposed? Are they infected? Or are they recovered from something like COVID? And then in that case, my transition matrix really just describes paths through a state machine. Because once you tell me each person what state they're in, I have some probability of transitioning to the next state in the sequence. So here, what I'm plotting is actually from a very recent paper where what they do is they do a version of this, but much higher dimensions, where what happens is they have an age stratified SEIR model. So they have potentially different parameters for the underlying state machine, depending on which age bracket you fit into. And then you try to find a good fit to the actual spread of things like COVID. So let me do one more cool example before we get into the math. So here's another fun one that I learned very recently, which is they have some pretty awesome applications in areas like medicine. So let's say that I've got, two drugs and I want to test out how effective they are. Or maybe I just have one drug and I want to test it against the placebo effect and figure out how effective this drug is. Well, one of the standard things that you do in clinical trials is you form what's called a randomized control trial. So here I take some cohort of patients, which hopefully are very similar to each other in some way. And then I randomly divide them into two groups. One group I give the actual drug to, the other group I give the placebo to. And then I measure the health outcomes across these two different groups as a measure for how effective the drug is. Now, the trouble is that, in randomized controlled trials, especially for very rare diseases or, things which affect people in a very individualized basis, it's hard to get evidence from a randomized controlled trial. Because, when you think about things like pain medication, the way that they work really has a lot to do with particulars of you, the individual. So one of the things that people have been thinking a lot about these days are what are called N of 1 trials. So what happens if I can't actually create a large cohort of patients? Maybe I just have you, and I want to figure out how effective the pain medication is on you. So in that case, one of the things that I can still do is I can use the time dynamics. So I can take 2 different pain medications, and every week, week to week, I might choose randomly which of the 2 things I give you, the actual medicine or the placebo. And then I measure some kind of time response for, how your symptoms are evolving. And I try to reverse engineer what the underlying linear dynamical system is as a way to figure out, how effective the drug is. So there are lots of other applications. There are things like speech processing, econometrics, and finance. But hopefully you get the point that these are very powerful abstractions. But just to go back to these 2 defining equations, right, for a linear dynamical system, really, there are 2 problems that we care about, right? See, one of the problems, which is maybe the most famous in this literature, is about what happens if I give you the parameters of the underlying system. I tell you everything there is to know about the underlying linear dynamical system. I tell you the A, B, C, and D matrices. I even tell you the law of the process and observation noise. Then one of the things you might ask is, if I observe the inputs and outputs of the system, how well can I actually estimate the hidden state? That's the kind of thing that you're doing when you're tracking the motion of the spacecraft, because you know what kind of inputs you're applying to the spacecraft, and you want to figure out where it is at every time step. This is a very well-studied problem, and there are great answers for this. But really, my focus will be on the question that comes before that. So in a lot of applications, we don't have this first principles way of thinking about what is the underlying set of parameters. In other applications, especially in natural processes, these are exactly the things we want to learn. Given one long trajectory from this linear dynamical system, is there a way to estimate the parameters of my system so that I can do the later downstream tasks like performing inference? So that'll be my focus for this talk, and I'm going to give you an exciting new algorithm for it. But let me try and make this problem precise first. So, first I'll state this a little bit informally, and then we'll dig into it a bit more formally. So I'm going to make my life as difficult as possible. I'm going to study the following learning problem. I'm given one very long trajectory from an unknown linear dynamical system. I observe the sequence of inputs and outputs to the system, and my goal is to estimate all the parameters that determine the underlying LDS. Now, one of the things I should mention is that even though these are called inputs and controls, it's a little bit of a misnomer sometimes, because in the learning setting, usually you just assume that they're disturbances. So I'm going to think about these as stochastically generated, maybe just from a Gaussian, and all of our learning algorithms will go through even when we're not allowed to actively choose these. But let me try and make this more precise, because see, one of the challenges in making this precise is that at the end of the day, I want to learn estimates A hat, B hat, C hat, and D hat. But the question is, how should I measure the closeness of my estimates to the true parameters? Sometimes what happens in many problems, especially in this one, is that there are invariances of the underlying parameters, and I'm only going to be able to get close up to some class of invariances. So let me try and define what's the formal problem by thinking about what the right invariances are. Yeah. Yeah, please.
So like the N-to-1 trial, I mean, doesn't that correspond to only learning A and B? Like, why do I need to learn C and D?
That's right. So in many of these cases, you can study them in all different models, right? So C could be the identity, and then it would be perfectly interesting. But the point is just that it's a pretty flexible model where I can study lots of these things.
But does it get easier if I only need to learn A?
It does, definitely. All right. So, here's a notion of what it means for 2 linear dynamical systems to be equivalent. Like, what if I have the true parameters A, B, C, and D, and I have my estimates A hat, B hat, C hat, and D hat. So here's a very strong notion of equivalence, is that imagine that I have some adaptive way of choosing my inputs. My next input, ut plus 1, is some arbitrary function of whatever happened in the past for my observations and my inputs. And the point is that I'll say that 2 linear dynamical systems are equivalent if they generate the same law on the trajectories. And then what I claim, the thing I'm not going to prove, but I'll give you a little bit of intuition, is that when you have Gaussian noise, there's this very nice relationship that 2 sets of linear dynamical systems are equivalent if and only if there's a change of basis that makes their parameters the same. See, the point is that in a linear dynamical system, I never see the hidden state. So I can actually reshuffle the hidden states as long as I undo that when it's time to actually measure the hidden state, as long as I undo it at the time where I think about how the inputs affect the hidden state. So these are just the natural transformations, which, because I never see the hidden state, the problem is invariant to. But my point is that this actually defines a very natural parameter distance for a very strong metric. Is that now what I want to do is I want to learn A hat, B hat, C hat, and D hat that are close with respect to this metric. So this is my problem. This is the formal problem that I'll be interested in, is given one very long trajectory, is it possible up to epsilon accuracy to learn all of these parameters up to the natural equivalence, up to U? All right. So in fact, what I claim is that even though this problem's been studied for a very long time, for over 50 years, it turns out that it's not just the algorithmic problems that are open, it's even the statistical questions. One is this information theoretically possible that are wide open. So it's no exaggeration to say that I think, for reasons I'll get into, probably over the last 10, 15 years, there have been 1,000 or 2,000 papers on this topic, which is kind of incredible. And it's basically the wild west of assumptions. You look through all these papers, and there are all kinds of crazy conditions that show up. But I can't go through and explain all of those conditions in each one of those papers, but I can tell you one condition that arises in virtually every single one of those works, which I don't like, and I want you to not like either. So let's talk about that condition. So what I look at, remember, the transition matrix A is the key. That changes a lot of the properties, especially in the long-term behavior of the linear dynamical system. What I'll be interested in is what's called the spectral radius. So the largest absolute value of any of its eigenvalues. When the spectral radius is strictly less than 1, we say that the LDS is strictly stable. When it's less than or equal to 1, we say that it's marginally stable. So at first glance, these two things might appear very similar to each other because they just differ whether the inequality is strict or not. But what I claim is that there's a world of difference between these two. So let's try and unravel them. So first of all, what I claim is that strict stability fails in the most interesting and important cases. In fact, we've already seen that. So if you remember when I told you about the spacecraft motion, right? So how did we get the transition matrix was by discretizing the continuous mechanics. And what's going on is that that matrix we got was upper triangular with ones along the diagonal. So does it have eigenvalues strictly less than 1? Definitely not. In fact, it cannot when it's the discretization of some very natural continuous process. That's bad. In fact, what's even worse, which is really the fundamental thing, is that if you think about it, what strict stability is really imposing, it's imposing this property that there are no long-range correlations. Because if I tell you the hidden state, maybe at the start or at some very distant time in the past, I can ask you, how much does that affect your estimate of the hidden state right now? And the answer is very little, because the influence of that state in the past is damping at an exponential rate, right? So in fact, related to that, even though I set up my goal as I want to learn from just one trajectory, in effect, what's going on is because the underlying system is mixing and forgetting the past, I get as many fresh samples as I want. I just have to wait for a bit. Now, in contrast, marginal stability is really just a kind of trivial assumption that makes the problem well posed. See, if marginal stability did not hold, if you had spectral radius strictly larger than 1, then as time goes on, your system is just exploding off to infinity. It doesn't even make sense to think about some fixed amount of process or observation noise because they're just becoming incredibly tiny. So this is really what you need to know to make the problem well posed. But if you think about it, what's going on is that hidden under all these bounds is really some term that looks like 1 over 1 minus rho of A. And all of these papers, their bounds degrade as rho of A approaches 1. So the question I'm really interested in is actually a conceptual question, which is, what happens when we're learning from dynamics? Do long-range correlations fundamentally obstruct learning? That's my goal. So I told you what results I don't like. Let me tell you what assumptions I do like, because you do need some assumptions. And the good thing is that these assumptions will all be things that are essentially required, information theoretically. So, the first one involves a block matrix that's called the observability matrix. So remember, A is the transition matrix. C is the matrix that describes the relationships between my observations and the hidden state. So what I'm going to do is I'm going to form this block matrix that looks like C, CA, CA squared, and so on. And what I claim is that if this observability matrix is degenerate, if it doesn't have full column rank for all orders S, then you're sunk, information theoretically. So let me just explain how this works at an intuitive level so that this makes some sense. So what does it mean for this to not have full column rank? It means that there's some vector Z in the kernel. So what's going on is that if I take some hidden state xt, but now I hypothetically move it in the direction Z, the trouble is I can ask what effect that change has on my observations. The trouble is that when I change the state from xt to xt plus Z, well, Z is in the kernel of C, so there's no difference. These two things are equal. That change had no effect on my immediate observations. And in fact, that's true for my next observation too, right? Because when I look at the effect, not immediately, but on the next state, xt plus 1, and then how that affects my next observation, again, Z is in the kernel. So again, there's no effect. So essentially what's going on is that when you don't have full column rank for this observability matrix, there are directions that the hidden state can move in that you do not see for a very long time or maybe ever. So the same type of thing happens with controllability, that I can form this block matrix. Remember, B describes the relationship between my inputs and the effect on the hidden state. So I form this block matrix that looks like B, AB, A squared B. And when this does not have full row rank, the trouble is that there are some directions that my input can never move me within. So it turns out that both of these assumptions are necessary, at least when you look at the infinite version, when you go out to infinite order. And this goes back to the work of Kalman in the 1960s. But what I claim is that those are the only assumptions you need. So it turns out that as long as you assume some kind of condition number bound, that the condition number bound of the observability and controllability matrices are bounded, then there's a polynomial time algorithm for learning linear dynamical systems. And in fact, the running time and sample complexity are going to depend polynomially on all of these condition numbers. And then the other fun thing is that, these assumptions aren't an accident. They're really what you have to do. So there's an almost converse to this statement that if your observability and controllability matrices are ill-conditioned for all orders S, then it's not your fault the algorithm doesn't work. It's information theoretically impossible. So let me say some philosophy before I get into any math. I think I still have a bit of time for math. So there's only one paper I know of which actually assumes marginal stability. So this nice paper of Simchowitz, Bokar, and Recht. Now, unfortunately, their hidden constants have an unspecified dependence on the system parameters. So for example, the dimension. So in fact, these things are exponential time algorithms, even in cases where we get polytime. But I also want to mention another philosophical tidbit, which is, why was there so much interest in these problems, around the dawn of control theory? And then there was a bit of a lull, and then it became very popular again, all of a sudden recently, was because of connections to things like recurrent neural networks. So the point is that linear dynamical systems can be thought of as a linear analog of that. And so what people wanted to do is they wanted to analyze gradient descent on recurrent neural networks, but failing that, they used LDSs as a prototype to try and build their intuition. But one of the problems with that sort of agenda is that you're really trying to do two things at once. I'm trying to analyze an algorithm people use in practice, gradient descent, and I'm trying to understand what are the algorithmic limits of solving this problem. And when you conflate those two goals, you accidentally miss a lot of crucial things. Like what I claim, and I'll make this as a punchline for later, I claim that the problem is dead trivial under strict stability, and it's a very, very simple thing. So I'll just leave that as a bit of a teaser for later. So in the short time I have left, I want to give you a teaser for, yeah, I have, I'll use it. So let me tell you at least, some key technical nuggets that I want to get to. So in fact, there's the standard way that we do learning theory, at least a lot of the learning theory that I know and I'm familiar with. And it really follows this blueprint that goes all the way back to Carl Pearson. And the idea is that, I want to learn some underlying distribution. what I'm going to do is I'm going to estimate moments from that distribution using my random samples. And then I'm going to set up some system of equations that, based on my moments, constrain the unknown parameters that I want to learn. And then some way, somehow, I solve that system of equations, and I prove that maybe it's got provably good estimates for what I wanted to learn. So this is the paradigm behind all kinds of things. This is, the state of the art in terms of what we know for provable guarantees, for learning things like hidden Markov models, mixtures of Gaussians, topic modeling, robust estimation. And what I want to know is actually another conceptual question, which is there a way to get this blueprint to work, not in the classic setting, but in this new setting where the data is non-stationary? So is there a way to get the method of moments to work when I have some kind of underlying time dynamics? So here's what the blueprint is going to look like. First, there's one more block matrix we care about, which is called the set of Markov parameters. This really captures the input-output behavior of my system, right? Because it captures, if I have an input at some time, what's the time-lagged effect on the output? But in any case, my two-step algorithm is just going to estimate the Markov parameters from samples, and then it's going to use the Markov parameters to actually learn the underlying A hat, B hat, C hat, and D hat. So this is what my algorithm will be. In fact, there's good news, which is, I'm pretty lazy, and the second step was already done for us in the 1960s. So what's cool is that there's this old algorithm called the Ho-Kalman algorithm that solves this problem. Given the Markov parameters, there's some tensor decomposition style approach for how to actually estimate what I really care about. So we can take that as given to us. In fact, there are even stability bounds for it. But what I want to talk about is really this remaining challenge. Usually this is the easy part when we talk about learning, is estimating things like moments from data. But it turns out that estimating the Markov parameters from data is really where the heart of this learning problem for linear dynamical systems is. So let's do that, okay? And what I'm going to do is I'm going to have some fun with it. So first, I'm going to convince you that it's completely trivial, and I'll be lying to you. So someone's got to catch me, or we can stop early, whichever. So here's a very simple observation. Say I told you the Markov parameters are the input-output behavior of the system. That's literally true. So if I take the input at some time t, and I look at the time-lagged output, yt plus j, and I look at the covariance between these things, the input and the output, what I claim is that as I vary j, I sweep out all of the Markov parameters. So once you make a claim like this, right? And I'm working here in the case where the inputs have identity covariance, but these things would generalize to any fixed covariance. But once I make this claim, there's really only one way to prove it. There are two equations, you write them down and you just kind of mess around with them, right? So for example, if I take j equals 1, when I want to say that the covariance is c times b, let's check why that is. So I write down one of my defining equations from the linear dynamical system. I'm looking at the covariance between yt plus 1 and ut, but I don't see any ut's here. Somehow the ut is baked into xt plus 1, right? Because it had effect on the hidden state. So what I can do is I can unroll what xt plus 1 is, and then I'm going to get my ut sitting out there. And I'm going to have the cb term because I've unraveled what xt plus 1 is. But now ut is independent of all these other terms except for the second one. So that's the proof. That gives me exactly what I wanted, that there's a simple unbiased estimator for the Markov parameters. And of course, in the 1960s, Ho and Kalman solved the rest of the problem for us. So now it sounds like we're done, right? So just to belabor the issue, this is an unbiased estimator of this. So what do I do when I have unbiased estimators? I just add them up and average, and that should improve the variance, right? So that's my unbiased estimator, and hopefully this is going to converge very quickly. Am I lying? Yeah. Oh, they're not independent. That's right. They're not independent. That's actually the whole point, right? So that's the whole point of linear dynamical systems, is that there's a time dependence. So who is to say that the variance of this is actually decreasing? It's not, right? Now let me make good on another promise. I told you that in these thousands of papers on learning linear dynamical systems with gradient descent, they inherit all of these assumptions. which somehow either directly have strict stability or imply strict stability. What I claim is learning under strict stability is trivial. Why? Because you can just wait long enough. So once you have strict stability, remember it mixes if you wait long enough. So yeah, instead of averaging over all the time steps, I take the average at, I take the value of the estimator at one time step. I wait a long time. I take the value at another time step where it's basically independent. And I keep doing this. That's why they all have this 1 over 1 minus rho of A, is it's really this in disguise, right? So let's try and do better now that we know that. So here's what's kind of fun is let's take control theoretic insights and turn them on their head. See, the issue was that I couldn't control the variance of my estimator because of the time dependencies. But control theory gives me a lot of tools for how exactly to tame how the dynamics are unfolding. Usually we think about that as injecting different controls to keep the system bounded. But maybe I want to think about it as some other way of stabilizing the underlying trajectory. Because the point is that, maybe I have this trajectory YT that gives me an unbiased estimator of what I want. But what I want is some other time series that still gives me an unbiased estimator, but I can tame it to prevent its variance from blowing up. So maybe there's some way to guess some good coefficients Cj that make this work out, right? So what do I want? Is I want some way to guess these coefficients Cj so that I preserve the fact that my expectation is unbiased. Because at the end of the day, I still want some other estimator for the Markov parameters, but I just want them to be derived from the y hats, not from the y's. But now what I want that's different between y and y hat is that I want the variance to be independent of little t of this estimator, which is the thing that failed when we talked about the other case. So, there'll be a few attempts, but really this one is the one that explains the meat of what's going on. So, here the idea is, again, the transition matrix plays the key role because that describes the long-term behavior of the system. So what I can do is I can take that matrix A. Let's pretend I knew it, which I don't. And let's say that I take Cj's to be the coefficients of its associated characteristic polynomial. So the key thing really is this fact from linear algebra, the Cayley-Hamilton theorem, which tells me that I take any matrix and I plug it into its characteristic polynomial, and I get out the all zero matrix. But what this really means, which is the version of it that I want to think about, is that it gives me a way to express A is an n by n matrix. It gives me a way to express A to the n as some linear combination of lower order powers of A. That's really what's going on in the Cayley-Hamilton theorem. So the point that I claim is that if I engineer my time series this way, if I choose the coefficients that induce the y hats to be from the characteristic polynomial of A, then the point is that it's going to cancel out all but the transient terms. So again, there's only one way to prove this. The proof is very simple. It's just a mess of an equation. So in the beginning, I tried to write a slide where I put the entire equation on, and then it ended up somewhere over here. So if you'll allow me some simplification, let's just pretend this was our underlying linear dynamical system. I'm simplifying it because there's no process and observation noise. I set D to be 0. But let's see the fact that I'm asserting that when I choose the Cj's to be the coefficients of the characteristic polynomial, that I cancel out all but the transient terms, just in this simple case as a proxy. So what do? I remember how y hat t plus 1 was generated. It's some function of the yt's, right? And now what I'm going to try and do is I'm going to try and organize things to group together the different u's, which of course are baked in to the y's. So I unravel the thing once. I express, the yt's in terms of the xt's. Xt plus 1, xt, and xt minus 1, and so on. Then I organize them and expand the xt plus 1. That'll give me a ut and an xt. I'm going to keep the ut on top because I'm really trying to create cancellations in the ut's. I expand these two terms. I'm going to get ut minus 1s and xt minus 1s. I expand these. I create ut minus 2s and so on. And now we can think about what's going on in this picture, right? So really, there's no hope of canceling out ut because there's only one ut. I have nothing to cancel him out against. But when I look far enough down into this block matrix, right? Eventually what's going on is I'm getting higher and higher powers of A, along with lower powers of A too. So that's the point, is that the coefficients were chosen exactly so that I can express the higher power of A in terms of lower order powers. And that's why eventually in this matrix, I'm eventually going to get cancellation. So if you work this out, what's really going on is that I get some expression that looks like this in the simple case. And eventually, I have all of these ut minus i's for I, large enough. They're all going to cancel out. Those are the non-transient terms. These are the transient terms that survive. The key point is how many of them are there? Well, there's only a polynomial in n number of them. So that's creating a variance that depends on all these parameters of the system, but not on little t. That's the thing that allows me to control the variance. Is now we're in sort of good shape, is that the variance is bounded independently of t. Now that's not quite the final solution for this, right? Because, unfortunately, I've messed up my expectation. So before I had that this estimator was an unbiased estimator of the Markov parameters. Now I claim I've messed that fact up because when I look at the equation I wrote on the previous slide, if I look at the covariance between y hat t and ut minus I still have the Markov parameter sitting in there, but I have this entire mess right here too. That's bad. I've corrupted my unbiased estimator. So there's actually a very simple fix, which is just wait, be lazy. See, the point is, if instead of immediately trying to cancel out, the previous y's from yt, what if I just wait r steps before I actually use them? Now the point is that ut minus 1 literally does not show up in the second term. It's just not here because it hasn't happened yet. ut minus 2 does not show up here because it hasn't happened yet. The same thing is true all the way out to some parameter ut minus k. So that's the point, is that if I want to estimate k Markov parameters, I just have to wait some larger than k number of steps before I create the cancellation, but I can still create the same kind of cancellation. So, I still need one more attempt. So the issue is that I lied to you. Sorry. See, the issue is that no one told me that the coefficients of the characteristic polynomial are bounded, right? In fact, that's another type of assumption that shows up in all these literatures, is some kind of assumption that controls the coefficients of the characteristic polynomial. But the good news is that's not what I need, right? So what's going on is that really in that expression I wrote there, I really had expressions that looked like c times a to some power times b should be canceled with lower order powers of a, but still with c and b sandwiching. So really what's going on is that in order for good coefficient c to exist, what I really need is bounds on the condition numbers of the observability and controllability matrices. Those are the things that imply that there actually is a good bounded coefficient way to create the cancellation. So, if you believe me with all these things, we're almost done, and yet it seems like we haven't made any progress yet. Because remember, my goal was to learn these underlying observability and controllability matrices, the Markov parameters. So somehow the thing that I've sketched for you is that if we already knew those block matrices, there would be a way to find good coefficients Cj. But isn't my whole goal to learn these O and Qs? So it turns out that this isn't circular. The way to think about it is really through convex programming. Because the point is that what I really showed you was that good CJs exist. If you told me what the parameters of my LDS were, I could figure out what good CJs would work. But now I can write a convex program to search for them. At the end of the day, I'm going to look for coefficients that are bounded and have the property that when you apply it as a transformation to my time series, that the time series remains bounded for all t. And the thing that you can prove, which takes a bit more work, is that you can define some kind of potential function that says that the only way that this is small for all t is if you've really created the right kind of cancellation, where my new estimator actually does have good variance, but that's how the overall algorithm works. So that's my proof, and we're roughly right on time. Let me just mention, what I hope you got out of it. So I introduced to you what linear dynamical systems are. They're a really cool abstraction. Really, you should think of them as some kind of like dynamic version of all of our favorite questions in learning theory. They have wide-ranging applications, but what I did was I gave you a new algorithm based on the method of moments to learn them that works under essentially minimal assumptions. One of the things I'm really personally interested in is that this is in some sense the beginning of the parallels between learning theory and control theory. So I can ask this kind of question for all kinds of other problems. You know, mixture models, change point detection. Are there dynamical analogs of it? And can the method of moments play a role? So let me stop there, and thanks for your attention. I'll take any questions you guys might have.
We have time for a question. Yeah, go ahead. So you mentioned in the prior work this issue that as you send the norm of A to 1 or spectral radius 1, everything blows up. So in this work, what happens if I take the spectral radius of A to 1? How does that change the bounds you have on the condition number? Do they explode, or what happens?
Well, so I mean, under marginal stability, they won't. So the condition number is really just saying that you have a lower bound of the smallest singular value. Now, the truth is that if you weren't marginally stable, but your spectral radius were larger than 1, it would actually make the problem easier, not harder. It's just that it's sort of not a very well-defined problem because my noise is remaining fixed and my system is exploding. So the only case where you'd have to worry about the upper bound for controlling the condition number is really when the spectral radius is larger than 1. And that's a problem which, for technical reasons is maybe, it's a little bit dicey whether that's the right version of the question. Now, there are other extensions, like we can do things like learning mixture models for this, where you get short trajectories from one of many possible linear dynamical systems. Those cases, because the trajectory is short, it's fine to allow the spectral radius to be larger than 1. And then it becomes a little bit subtle. The other thing is like, do you give me the order S at which the thing is well conditioned, or do I have to determine it? I would kind of hope that the ultimate way to do these things is really in a non-parametric setting through some kind of transfer function, but I don't know how to do that yet.
I think the noise needed to be independent of the observations for this.
That's right. That's right.
Any hope of relaxing that assumption?
Well, you could definitely relax this because as long as there's some bounded dependence, you might still be okay. But the trouble is, like, I don't really know a clean model that one would pose there. Somehow, if the noise is really arbitrary, then it seems like it should be hard. But I kind of don't know what's a good target to aim for between those two things. But it's an interesting question for sure.
What is the dependence on the spectral radius?
On the spectral radius of A? Yeah, so here we just need rho of A is less than or equal to 1, and we don't have any of these 1 over 1 minus rho of A things. So that's the point, is like we don't have any direct dependence on the spectral radius. We just need bounds on the condition number of observability and controllability. And those are the things that there's this almost converse to. All right.
Thanks again, Ankur.